All right, so now that we know how to sort of work with matrices and what they're doing, let's have a look at a practical use of them in 3D. So I'm going to show you a simulation I have here. We've got our normal kind of crag animation that comes default with Houdini, and he's essentially bursting his way through some wood over here, right? So it's just smashing it, and you can see it fractures and splinters the way we would expect wood to break, okay? And the way we achieve that normally is to essentially scale down the object in one axis, the axis that we would expect the grain to be running along. We Voronoi fracture, and then we scale back up by the inverse amount. Okay, so that is typically the trick that we use to get splinters. But the problem with this situation is that I actually have pieces of wood, like planks of wood, that have different orientations, right? We have some vertical pieces, some horizontal pieces, and then even a few diagonals, right? And even the top and the bottom of these two sort of, this like split door over here, are oriented slightly different around this y-axis as well. So with this variety of orientation, it is very hard to fracture this correctly, because if we just scaled this door down along y, fractured, and then scaled back up, then the splinters would be fine on these vertical pieces, but the diagonals and the horizontals would not be broken correctly. You'll see here, let's pause on here. At the top, you can see that the splinters are running along the plank, the direction of the plank. Same as in the diagonal, you'll see that they have the splinters run along the diagonal, and then on the vertical, they are vertical. And that's what you'd expect to see. So in this situation, we can't just scale the whole thing and fracture. We have to figure out the orientation of all of these pieces in order to reverse that, fracture with all the pieces essentially aligned at the origin, and then put them back. Because when all these planks of wood are cut, they are cut along the grain, all of them, when they're created as planks. And only when assembled into this door do they then have a variety of different orientations. Okay, so let's take a look in Houdini how that would be possible. All right, so here I have my door. This is the kind of final result of the sim. And I'm going to show you here how I've built this. So in the subnet, right, I've got a few, it's just a box that I've essentially scaled and transformed and turned into this shape, okay? Now, if we wanted to just fracture this, I mean, right here, I already have these kind of transformed pieces, so I know the exact orientation of these. I know how many degrees I'm rotating the diagonals by, and, you know, so if you already knew that, you could sort of more easily go and just fracture before creating this door, or maybe just, you know, drop down a transform here with the reverse of the rotation, then do the fracture, and then apply the rotation again. So there are a few tricks we could do in here. The reason I'm not going to take that route is because we don't always have access to this. Okay, most of the time we're not modeling directly in Houdini. We get given an alembic, or you know, some kind of, you know, like an FBX or whatever it is, and we just get a piece of geometry. So it comes to us like this, right? On the subnet, I've got points and primitives and vertices and everything, right? It's not packed. There are no groups. There's no attributes that are going to help me, and, you know, it's essentially, there's no transformation information, nothing. Okay, if I look on my points, like, there is absolutely nothing to help me figure out how this is oriented. Okay. I mean, even if we look here, there's no transformation in the prim intrinsics. There's literally nothing. But what we're going to do is write some, like, sort of build a system that's going to help us figure out the orientation of all of these planks of wood. And then we're going to use that. We're going to store that as a matrix and use that to kind of reverse it, fracture at the origin, and then go back. Okay. So I just want to start, before we deep dive into how to figure out the matrix side of this. I just want to show you here what the principle is, in case any of you haven't done this before. So let's say we've got a plank of wood like this. Okay, so that's our plank, and we want to fracture this. Now, when we scatter points, okay, and I never like relaxing it. I don't know why that is on by default. Anyway, so we would have some scattered points. We're going to use this to fracture. So if we put a Voronoi fracture node down, feed in the geometry, feed the points, and you'll see here that it has, so if we look at the, well, we can look at the name, yeah, we can visualize name and you can see the color then, okay? So that's what our pieces are coming out like, essentially. And that doesn't look very much like wood, okay? Maybe these would be sort of concrete pieces. I mean, obviously you want to always avoid these normal kind of Voronoi shapes, especially if you do like an exploded view here. When you see this, these shapes, it looks very obvious and very bad, okay? But there are ways of going in and adding some noise or creating higher res fractures that we then place back on top of here. And, you know, so there's other methods of kind of making this look more like, you know, concrete when it smashes. It kind of gives you these rounder shapes, okay, with flat edges. But when it comes to wood, we need something a bit different. So we would drop down a transform here, and before the actual fracturing of it, and even before the scattering, okay, we want to essentially scale this down. And the reason for this is because then after we fracture, when we scale back up, we're essentially stretching all of those pieces. But we want to scale down and up by the inverse amounts, because obviously we want to maintain the overall scale of our object. So if I just paste this in here, the relative reference, then it's double transforming it. But instead, if I invert this, okay, and you can do that by either just clicking invert transforms over here, or because we know how to do inversions, we can do that, right? So it's just 1 divided by. So really simple. So now you'll see procedurally, without touching anything, I can, as I change the scale, the object is actually not changing scales, but the pieces are getting longer, because they're actually being scaled down, then fractured, then scaled back up by the inverse amounts. So it's, it remains perfect. Okay, and this is how we get these kind of thinner pieces for our wood. I mean, obviously you need at least enough pieces for it to look decent. So generally that is also going to be a thing with this, is it needs to be quite a few. And then we maybe make these even a little bit longer. And then we start reaching something that looks kind of like wood, right? I mean, especially if it's reassembled like this. Let's take away that. And then if we had to go and just grab a selection and delete, you'll see that that starts to look very much like splintered wood. Okay, maybe a bit of noise and things we would add in the shader, but ultimately this is going to sim pretty well. Okay, and because it's Voronoi, these are convex pieces, which is great and easy to sim. Okay, so now that we know that, let's look at the much more complex system here, which is how we're going to figure out the orientation. Because you'll see in here, we've kind of got that happening inside of our loop, right? We're scaling, fracturing, and then scaling by the inverse amount, right? So really this is, we already know that part of it. The complex part is really just figuring out the matrix, because once we have the matrix, it's easy. We apply the inverse matrix, so it'll go right back to the origin, and then we work there and then apply the matrix back on, okay? And then afterwards, everything that's happening at the bottom here, I just want to point out, is very, very simple as well, because we're just assembling and kind of essentially choosing which of our pieces are active and which are not, and setting up constraints. And all of this is just a normal part of doing rigid body sims. So none of that is actually complex. So I'm not going to go over it in great detail. I'll briefly go through it at the end, but really the main thing that's happening here is inside of this loop. Okay, so this is where we're going to focus our attention. Now, after taking our sort of base geometry, the very first thing I'm going to do is create normals, and I'm going to make sure that they are vertex normals. This is vital for when you're doing fracturing, because if you have point normals, they cannot represent multiple directions at like a sharp edge. So they will be faceted instead of cusped, right? So you will always see the seam, okay? And that's not what we want. So you need to have vertex normals, and it is better to create them before we do the fracture, okay? And then what we're doing here is we're running connectivity. So we're using a connectivity node because we're assuming that we don't have groups here. We don't know like sort of which objects are actually connected as one piece. Okay. So, obviously if you have groups, that's great. Then you don't need to use a connectivity node. You can just loop through your groups or whatever, but, or maybe if you've got packed geometry, then that helps you already. But we're assuming the worst here. We're kind of doing worst case scenario. You don't have any of that information. So the connectivity node is going to help us essentially separate all of these pieces into all of this connected pieces. And it gives us a class attribute. So you'll see here each piece and all of its connected neighbors are its own class. Right. Okay. So now when we dive in, okay, let's go here. So we're going to loop through all of our pieces based on class, right? So we have within that, let's take a look at the actual class. Okay. There are a bunch of points that have 0, 1, 2. You see, it's just an integer and it goes all the way up to 31. So we have 31 different pieces here. And so we're going to loop 31 times. Okay. Now, don't get confused here. I have included this all in a compile block. That's just because none of the nodes inside are sort of non-compilable. So it does make it faster at the end. But you don't need to include the compile block if you don't want. In fact, you know what? Let's just not confuse things. So let's get rid of the compiling just for now. But you can, if you want to, include it in a compile, and then you just tick on multi-thread when compiled, because this should be compilable. Okay. So anyway, to keep things basic, we go into a for each loop, and we're looping through our piece attribute, which is class. Now, if we can obviously do it through all the pieces, and then that takes a little while, okay, but then it does work. But what I'm going to be doing is ticking on single pass so that we can look at just a few examples of individual pieces and how those are handled. Especially we want to check whether our system works on verticals, horizontals, and diagonals. So we're going to be checking 4, 1, and 0 as our ways, sort of proof that this works. Okay. Now, let's start with this diagonal because this is kind of the most difficult, and this is going to help us figure out what the system is that we're going to use. So in order to figure out how this is oriented, what we would ideally want is for this to be a perfect cube. Okay. But if it was, right, so if it didn't have this sort of diagonal cut at the end, and if it didn't have more geometry on the inside, which in this case it doesn't, it actually literally is 8 points and it's a perfect cube, but the odds of us getting that is very slim. Most of the time it'll be subdivided, it'll have sort of like, extra loops on the edges and stuff, so it'll be beveled and everything. It just, we will get untidy geometry because it needs to look like a natural piece of wood. Okay, it's been nicely modeled, but we need to work with that. So one way to kind of get around that, because we need to work with the most simple geometry possible, is to use the bound. Okay, so we want to essentially take the bounds of the object and therefore turn it into just a cube. 8 points, nothing complex, just a cube. And the bounds has a really cool feature in here which lets us create an oriented bounding box, because if we don't do that, then what it does is it creates just a world oriented bounding box, okay, which is then for the diagonal is going to create a massive box. For the horizontal and diagonal, it'll be fine, it'll be perfect. Okay, it doesn't really matter to us. But because they already align, and so that it doesn't really matter. Although here we have, like I said, the top of the door and the bottom of the door are even rotated around Y a little bit, and that will mess with the bounding box as well. But by ticking on oriented bounding box, what this is doing is figuring out sort of the smallest bounding box that it can possibly create within that object. Okay. And so you'll see that even though we have the diagonals on the corner, it creates an oriented bounding box that encompasses the entire shape. Okay. so you can think of this almost as though what this piece of wood would have looked like before it was cut out on this angle and turned into the door. All right. So this is going to be the sort of pivot of what we're going to calculate. Okay. And then here's where we're doing essentially all of the orientation work. The rest of it is really simple. Here we're just going to essentially be applying the inverse matrix like we've discussed, and then doing the fracture, and then at the end applying the matrix back. Okay, so it's all happening in one wrangle. Now the theory behind what we're doing here is if we take a point, right? So for ease, let's say 0.0. Okay, we take our first point in our bounding box, and because we know that it's a bounds, we will always have 8 points exactly. At this point, if we look at it, it has, if we look at its sort of its neighbors, right, its neighboring points. So what we mean by neighbors are points that are attached by a line, by an edge. Every point in a cube will have 3 neighbors, okay? So 0 is attached to point 3 by an edge. It's attached to point 1 by an edge. And then it's also attached along this very long edge to point 4 at the back here. Those are its 3 neighbors. It only has 3, okay? It is not a neighbor of 2 because it's, you know, it would have to go through 2 edges to reach that. Okay, so you see how that kind of works. Now, if we look at the neighbors of 0, you'll see that they have very different proportions because essentially they represent the local x, y, and z of this bounding box. Okay, so there is a very short one because that is the sort of the thinness of this this plank of wood. Then there's the next longest edge, which is 0 to 1 over here, which is kind of the thickness of this, right? Like the width of the plank. And then the length of the plank is 0 to 4. And they are also 90 degrees to one another. That's really important to note. So remember our cross product, our reference frame, we have these kind of 90-degree angles to one another. And a bounding box gives us all of this. Because it is a box, you know, it's a cube, we know that every point, its 3 neighbors are tangential. They are 90 degrees, okay, so they're orthogonal, right? And then they represent the sort of local x, y, z. So that's all the information we need. So what we're going to do is we're going to take 0.0. We're going to calculate these, use these 3 neighbors essentially to create a reference frame. And that reference frame lets us calculate orientation, which is perfect. But the one small issue here is that we don't know, how do we know which one is the long edge? You know, 0 to 4, or is it 0 to 1? Maybe that's the long edge, okay? Depending on if we had very like wildly differently oriented pieces here, we may end up where 0 to 1, this edge is actually the long edge because maybe the piece goes this way. Okay, so it's, you know, maybe we have a crisscross planks. So the one plank would have 0 to 4 as the long edge, but then in the next one it would be 0 to 1 is your long edge, or whatever it is. Okay, so we can't just assume that we know which one is the longest. And we need to know those because we need to know which one to essentially make along our z, okay? In other words, which one is our up, which one is our normal, and which one is our tangent. We have access to all 3, but we don't know which one is which. And the order of those really matters when it comes to matrices. So here's what we're going to do. We're going to use the actual length of the edge to determine which one is which. Okay, so now that we kind of know the theory and what we're aiming to do, let's take a look at how we achieve that in Vex. Okay, so I'm creating a variable here called pos, which is just the position that I want to kind of reference because we're running over details, so we're only running once. And the reason for this is because if correctly calculated, the matrix of all of these points is going to be the same. Now that's not technically true because every point has its own matrix if you use itself as the center point. But what we're trying to do here is basically calculate the transformation of this whole object, this entire plank. And so what we want is one value. So we're going to run over detail and we're going to calculate this just once. It's also a very efficient way of doing it because there's no reason to recalculate this on every single point, right? We have one matrix for this entire object. So we use the point function and we look at point 0. We're like explicitly feeding it point 0 as the point number that we want to assess. And we grab its position. Okay, so pos is going to be a stand-in for v at p because we don't have v at p because we're running over detail instead of points. So we're never going to be able to use v at p, but we're going to use pos. And we also want to figure out the list of neighbors. So for that, we just create an array variable and we just run the neighbors function. We feed it point 0, so geometry 0 and point 0, and it will find all of the neighbors of point 0. And we know that that is always going to be 3, okay, because it's a cube. It will always have 3 neighbors. Okay. Now, so we are going to loop through the neighbors and build the vector array, okay. Now this is an array of vectors from 0 to that point. So 0 to 3, essentially that edge, we're going to subtract 0 from 3 in order to calculate that vector. And we need the length of that vector because that is going to tell us which is the very far, so like which is the length, which is the depth, and which is the width, okay? So we need the length of that vector, that's important, as well as the actual direction of that vector, because that's going to tell us, that's going to help us create our reference frame. So that's essentially giving us our orientation. Okay. So I'm creating 2 empty arrays before I do this. One is the vector array, which vec array is essentially the reference frame. So it is the normalized direction vectors for all of these. So from point 0, it'll just be our sort of normal, up, and tangent on these 3 axes, okay, but exactly normalized to 1. And then the length array is going to be the list of lengths of these edges, right? And we're going to use the length array to figure out which of these vectors should be used as up, which one should be used as the normal, and which should be used as the tangent. So I'm going to loop through all of the neighbors. Okay, so we do a for each and we'll run through neighbors. I have my index and I have the value. Now, because we're looping through neighbors, the value is going to be an integer, which is going to be the point number. So we're looping through and v is going to be in turn 1, 3, and 4. Okay. And when I know what that point number is, I just get its position. Okay, so point 0, then we grab the point position, but then we use v as the point number, okay, and then we subtract it from pos because we know that pos is the point position of point 0. So basically we go the position of point 3 minus the position of point 0. Then next time we loop, we say the position of point 1 minus the position of point 0, and so on. Okay, and that gives us our vector. Now with that vector, we can normalize it to store that as in our vector array, and we can get the length of that vector to store in our length array. So when we exit this loop, we have 2 arrays. This one is filled with 3 normalized vectors. This one is filled with 3 float values, which are the lengths of those vectors. And now here's a little sort of trick that we can do in Vex, which is we can create a sort order. So we run an arg sort function, arg sort, and we feed it one array, okay? So what it's going to do is sort this array in increasing order. And this array is easy to sort because it's just a bunch of lengths, okay? So we know it's easy if I gave you 3 numbers, right? Let's say it's 0.1, and then I give you 3 and 20. You could put those in order. But how do you put vectors in an order? I mean, you could have a really long vector, but all of its components are negative. So it's like, do you sort by the length? Are you sorting by the x component? Are you sorting by the y component? Are you talking about a number of components? Like what is it, right? So what we do is we're using the length array to create a sort order. When we sort these into an order from smallest to largest, the argsort returns that order for us. So it says that, oh, okay, I'll put the second one first, and I'll put the third one second, and I'll put the first one third. Okay. Now that sounds a bit complicated, but essentially what it gives us is an order that we can apply to our normalized vectors, right? So it's kind of like saying, sort this one, and then whatever you did to that, do the exact same thing to this one. Okay. So that's what we do here with the reorder function, is we're saying reorder this vector, sorry, this array, the vector array, but reorder it based on the sort order that came from sorting the length array. And so what happens is that it returns a sorted vector array for us, which is essentially the normalized 3 vectors here. So it's our reference frame, but it's sorted in such a way that the first vector is the shortest one. So in other words, the first one will be this one, 0 to 3. And then the second one will be 0 to 1. And then the third one will be 0 to 4. But it's basically procedural. It's based on these lengths. And so if we had to, let's say, randomize the point order, it wouldn't matter, because it would recalculate itself and still would reorder itself and find the shortest vector and make that the first one in the array. Okay, so it doesn't care about the numbers, it only looks at the lengths. Okay, and so this is very, very important. This is kind of probably the most complicated part of it, because now that we have that in order, we know which ones we want. Okay, and we want to sort in such a way that this long edge is our normal, because we want that normal to go along our z-axis, because then all of our planks are going to be lying with their length along that, and that z-axis is what we're going to be scaling by. So when we did the fracturing, where we said we scale down, fracture, and scale back up, well, we're going to scale on z. So we want to make sure that our planks are arranged so that they're lying along z. And also, we want to lie them flat. So now we're going to use our second longest edge, which is 0 to 1, as the up. Okay. And so that's how we're going to sort of, arrange this. Okay, so we can extract our 2 vectors. Now, we do have our full reference frame. We have 3 vectors, but we actually only ever need 2. Okay, remember, even when we do the lookat function, we've got a from and a to and an up. Now, the from and to forms one vector. So it's essentially asking for an offset and then a vector, basically. Okay, so these two combined, the difference between them forms a vector, and then this is 1. So it really needs only 2. The reason for having a full reference frame is that we know they're orthogonal, and we also know that we can then swap which one. If we want to change the orientation of these planks, we can simply swap the up with the other vector and so on. Okay. So we extract our normal by grabbing our sorted array, but we grab the -1 index. Now, if you've ever used arrays before, you'll know that -1 means grab the last item in the array. And because they're sorted in increasing order by length, the short edge is going to be first, second edge will be this, and then the third one will be the long one. So our third and final number, and in order to get our final, we use -1. And then to get the second last, you use -2, and that will be our up. Okay. So we could have gone, we could have called this 2 and this 1, because it goes 0, 1, 2. Or sort of more correct in terms of coding, we want to grab from the back end. So we go -1 and -2. Okay. So now we have our vector that represents our normal and a vector that represents our up. Okay. And so from this point, our normal is along here and our up is along here. Okay. And that's all we need. Now the rest is quite simple. We use our lookat function because there is no offset. So basically we're going to calculate our offset separately in our transform. So we're saying relative to the center of the point, so 0, 0, 0, we have our normal. Okay, so we feed it our normal and we feed it our up. So it's from, to, and up, gives us our look at, which is a matrix 3. But remember, when we want to combine our transform matrix and our rotation matrix, we need our matrix 3 to be converted to a matrix 4 first. Because we actually, when we multiply them together, we need to go rotation first and then translation, sorry. But if we multiply a rotation matrix first and it's a matrix 3, then the entire result will be a matrix 3, and so we can't have that. So we need to make sure that it's a matrix 4, which will have identity translations inside of it. Okay, this is all very similar to what we were doing in VOPs at the end of the last lesson, but this is just now how you would do it in VEX. So we run the look at, we convert it to a matrix 4, and we store it as our rotation matrix. Then, exactly like what we did in the previous lesson, to calculate our translation matrix, we essentially just create an identity matrix, and then we translate it by our position. Because we know the position of this point, so we know the offset from the center of the world, and so we're just going to calculate that. Now that we have these two, we've got a rotation matrix and a translation matrix. All we need to do to calculate our transformation matrix, which is all of it combined, we are going to multiply them together. Now we don't have any scaling because in this case we know that our scaling is 1. This is the size that the plank should be. So we don't need a scale matrix, we just need rotation and translation. We multiply rotation first because our order is important when it comes to matrices. Rotation first, then translation. And that gives us our matrix. Okay. And now I'm writing that out as a detail attribute. So here we're saying set detail attribute and writing this out as matrix. Okay. Technically we are on detail level, and so we don't have to run this function set detail attribute. We could just say 4 at, because remember 4 is the how we write a matrix. Okay, the same way that like v at is vector. Well, 4 is a matrix 4, so 4 at mtx equals, and then we would just reference our variable. So we could do this because we're on detail. The problem with that is that often in order to test some things, like if we wanted to see what our normals and our up look like, we have to switch into point mode to write that out, and then this doesn't work and you end up switching backwards and forwards. So while working with it, I found that it was much easier to just leave this as set detail attrib. Okay. So once we've calculated our matrix, we're just writing it out. Okay. And obviously the reason we need to write it out is because we're going to apply the inverse of it now, but later on we need to apply it again. So we can't just do the calculation in there and apply it to our points. And don't forget as well that we've calculated this on our bounding box, not on our original points. And this is important because maybe our original points could have like millions of polygons. It could be subdivided, and like we said, like it could basically be high detail or slightly warped edges. So we calculate this on our bounding box and then we transfer it to our points. So we use the detail attribute pointing at input 1, which is our second input. So we're pointing here and we're saying grab the matrix value from there, mtx, that's the name of our attribute. We have to be careful, we have to typecast it. Okay, it will not work if we do not typecast this, because detail doesn't tell it what type of attribute this is. It has no idea, so it just assumes that it's a float, which is incorrect. So we have to typecast it by wrapping it in a matrix function, and then we're inverting that. Okay, and then when we just take a matrix and multiply it by the point position, we get it at the origin. Okay, this is almost exactly like what we were doing in the previous lesson as well. And so you'll see it's disappeared here, but if I go and find it at the origin, okay, let's switch on our grid, you'll see that our plank is sitting here at the origin. Okay, it's up on its edge because we set that width as the up. If we wanted to lie it flat, we could come in and swap this here. So instead of referencing -2, we'd reference -3, and it would lie it down flat. Or instead of -3, you could say 0 as well if you wanted to. Okay, so you can just choose which one to use essentially, and it will then orient itself correctly at the origin. And you'll see here that it doesn't care that there's cut off edges. It's orienting it based on the bounding box. So even though the sort of edges are cut, it is facing correctly along the Z. Okay. And in fact, it's -Z, right? Which is correct. Okay. So that is how we want it to be aligned. And in fact, all of our pieces will now be aligned that way. Okay. So then we do our transformation. So you see here I'm just scaling it down along Z by however much I want the length of my splinters to be. I'm scattering, right? Now the only other fancy thing I'm kind of doing here is I've created a spare input. So just come here and add, sorry, I've lost it now. Oh yeah, add spare input. Sorry, I was blind for a second. Which adds an input here, and then we can reference our metadata node in order to get the iteration value from it. And the reason I'm doing this is just because we've got a lot of very identical pieces. If we don't change the seed based on iteration, then all of them are going to fracture the exact same way, and that looks kind of bad. So we want every time we loop through a piece, even if it happens to be cut to an identical length, we still want it to have its own random seed for the way it scatters those points. Okay, and the reason I'm doing it through a spare input instead of just in here referencing this over here is because you have to use the spare input if you want it to be compilable, and that makes it a lot faster. So make sure you do that if you want it to be compilable. Here we then fracture it. Okay, so we're just doing our normal fracture, and you can see our pieces in there. And then I'm scaling back up by the inverse amount. Okay. And now, so you'll see all of our pieces there. If I go here, and you'll see in our wrangle here, we're doing very similar to basically what's happening in this one, except without the inverse. So I'm just taking our point positions and multiplying by, and then I'm fetching the matrix value. And very, very important, I'm typecasting it as a matrix. Okay. So you'll see it applies the translation and rotation back to it. So if we go, if we go here, this is lying at flat, but you'll see the original is lying here. And when I go from the original to mine, they don't change because we've put it at the origin, scaled it down, fractured it, scaled it up, and then reversed the move to the origin. So now it looks exactly the same as it did before, except it's actually fractured along the grain. Okay, now let's test this quickly. We said we would test it on 4, which is the most difficult one because it's the one with the sort of skew cut edges, and it's the one on the diagonal. That's very tricky. Okay, but 0, which is a vertical one, okay, still works. So we still have our vertical splinters, which means that one's working correctly. Let's show you here. We grab the bounding box of it, calculate the matrix, then when we reverse it, you see it lies at the origin correctly. And then we scale it down. Sorry, there it is. Scale it down, scatter points, fracture, scale it back up. So we've got our splinters, and then we reverse the move. Okay, so 0 works, 1 works. You'll see here, splinters are going that way. That's another vertical that works. Okay, 4 is our diagonal. The diagonal works, and then these are even the small slats as well, the sort of thin slats that are all identical. And they still work even though they're thinner than the other pieces. And also you'll see that every time we, I'll show you here, if we display name, so you can actually see the splinters like this. And then we go I'll switch off single pass, so let it calculate all of them. Because we had that random seed changed by the iteration, now you'll see that all of these, even though these slats going here are all identical, they've got different splinter fractures, okay? Whereas if we took this away, cancelled that, then let it recalculate, and you'll see that these all become identical, which is obviously not what we want. Okay, so let's reset that. There you have it. So after that, all we're doing is assembling so that we're packing it back by pieces and creating packed geometry. So these are ready to be simulated. I'm transforming it because it was just a little large, so I'm scaling it down and getting it ready for the sim. And then I'm also creating an edge over here where it would be attached to the sort of door frame where I didn't want those pieces to move. So I'm creating an active value saying all my pieces are active, but then just on the static group I'm making them 0. Okay, so here's what our splinters look like. If I show you the exploded view, we've got our splinters going diagonal, horizontal, vertical, everything. Okay, and also here I have my constraints, which I've set up. Just connecting pieces and then setting my constraint name and constraint type. And that's it really. We jump into our sim. It's very, very simple. We've got a ground plane, a collision object, which is the character smashing into it. And we've got a glue constraint, which I adjusted the strength down a little bit and changed the data type to glue because then it matches the name on the outside that I gave it. And then in here, I'm just deleting all the broken pieces. Okay, so this is like a standard setup for doing fractures, right? Even if you use a shelf tool, it sets it up exactly like this. And we've got some gravity as well. Okay, loading in the points, and yeah, that's it. So then if we sim this, oh, and I'm simming only from the frame just before these starts to hit it, because obviously it takes a little while to sim this because there's so many pieces and they're all connected and they start to fracture apart, so it does take a while. And I've also had to increase, because he moves so fast, I have increased the sub steps of my sim. So you'll find it is a little bit slow, and you can see it's calculating sub frames, but it's necessary in order to get a correct kind of fracture. Otherwise he goes right through it and it doesn't fracture because he actually skips straight through in a single frame. Okay, but there we go. So now that's how you have wood fractures, and look at this, you get some really nice kind of splintering happening in there. Okay, I mean, of course if you went higher resolution you get much better results, but yeah, it's not bad considering we used a piece of geometry and didn't rely on any of the transforms in there, and just procedurally are figuring out the orientation of all of this. It's pretty cool. Now keep in mind, this is very specific to wood planks. Obviously if you have objects that are spherical or sort of equally high as wide as deep, then this isn't really going to work because we're relying on those differences in length in order to figure out which way's up. So if you had other objects, maybe you'd have to figure out a different way of figuring out which is up. Okay, so there's lots of ways we can do it, but this is just one way of handling quite a common thing we come across, which is, okay, like destroy a building and then all these pieces are wood, but they haven't been modeled with splinters. So now we can procedurally go and calculate the splinters. Right. So I hope you found that very useful, and I hope you found the course very useful as well. So I'll see you all next time.